All right, here we go, getting into chapter 6. So first lesson we're going to look at is our introduction to vectors. So you may have had some experience with vectors, depending on science courses you're in, but we're going to be starting out heavy on vectors, and then all this is going to bring in some trig to go with it. So we'll get to that at some point, but for now we're just going to start with our introduction to vectors. So for those of you who have not seen vectors before, it is a directed line segment, or we would see it as like an arrow. So if you look at this one right here, like an arrow, right? So basically it goes in one direction. So one of the qualities of a vector that you always hear is it contains two things. It contains magnitude, which is like its length, and direction, right? So those are kind of the two characteristics of a vector. So it has an initial point, and then it has a terminal point, and so the vector is always headed towards the terminal point. So whenever we name a vector, we always use the two letters from the initial point to then really any other letter on the line, right? As long as we start with the initial point. So we would call this one vector PQ. So our notation is going to look like this. Again, the magnitude represents the length of the vector. In terms of like physics problems, we can also see it as the force or velocity, right? Force or velocity. So those also kind of define the magnitude of a vector. The notation looks like absolute value bars. So if you ever see this like absolute value look for a vector, that's simply the notation for magnitude, and that just means find its length. So sometimes you'll see just this statement right here, and it'll say find this, and it'll just give you this look. And so we need to know that that means I'm looking for magnitude. So any two vectors that have the same magnitude, same length, and run the same direction would be equal vectors, right? So this statement is true only if they have both of those two things in common. As we look at our vector addition, so really popular idea that we'll be doing with vectors is vector addition. As you look at this diagram right here, so here's the question I'm posing is where would you draw the resultant of u plus v? In other words, here's vector u, here's vector v, right? So if I add those two vectors together, what result would that create? What vector, where would I draw the vector for the result of adding those two vectors together? So notice the initial point of u hits the initial point of v, and then it heads off into this direction. So as I put those two vectors together, what we're going to see is I will still have the same initial point that it started with, and I will have the same terminal point for where it ended. So altogether, it started here and ended here as I put those two vectors together. So the resultant would be this guy right here. So that would be vector u plus v. All right, so here's kind of the key on this that you'll see within vector addition is as you add vector u to vector v, the key that makes this doable that we can see an answer for is where the first vector ends is where the next vector begins, right? So vector u hit the initial point of another vector, and then it carried off into this direction right here, right? And so that's what allowed us to draw the result that said, okay, this is where we started, this is where we ended, so this is my resultant. We can do the same thing with two letters. So sometimes vectors are just given a name. They don't actually use like points on the vector. They just give it a name. So that's what happened with these two. It was just a title that they gave to each vector, vector u and vector v. But if we didn't have a title for it, then they would pick, like I did up above at the start of this lesson, I just identify the initial point and the terminal point of a vector, and that's how we give it its name, right? So they call this first one PQ. We are adding that to QR, and so what would be the result? Well, again, just like the one that you saw right here, it started, the initial point of the sum of those two vectors started at point P, and then it ended, the terminal point of the sum was right here at point R. This is where it eventually ended. So the resultant would be vector PR. that you're seeing right there. So when you see these equations, right, so if I were to say, okay, what's vector PQ plus QR, so with the result that I get, again, what you're seeing right here is you'll see that terminal point is Q. It meets up with the initial point of Q for the next vector. And so when I put those two things together, it's kind of like that middle piece is being removed and it becomes one big long vector. So it started at P and eventually ended at R. So we get vector PR. All right, so let me go down to how do you find magnitude or length? And that is just our good old-fashioned distance formula. Because it's a length from one point to the next, right? It's just the distance between those 2 points. So it's just basic distance formula. So I want to start with my initial point, of course, and then I'm going to end with my terminal point. So if I wanted to find the magnitude of vectors u plus v, that means I'm looking to this as my initial, I'm looking to this as my terminal, and that's what we're going to be plugging into this distance formula here. So as I look at this drawing, where is the initial point for vector u? And that is at 2, 2. Where is the terminal point of vector v? Looks like that one is at, I believe that is 6, 4. And so we're simply going to find the distance from where it started to where it ended, right? So essentially I'm looking for the length of this vector right here, which is vector u plus v, right? Just like we saw up above. So if we throw those into our distance formula, I'm going to do x minus x squared plus y minus y squared, all under a radical. You guys all super familiar with the distance formula. So if we do a little cleanup, 6 minus 2 is 4, 4 squared is 16, 2 squared is 4, so rad 20. And we'll just keep it as that for now. Of course, we could simplify that. We could turn it into a decimal. It just depends on what the directions ask us for. So but when you see magnitude, just think back to your basic distance formula or the length of that vector. Okay, so those were kind of my initial notes to help you sort of get started before we actually started doing some of these within our main part of our lesson here. All right, so on this one, they're identifying a couple vectors for us. So they're saying vector u is these components right here. Guys, this, by the way, is called component form. Component form, just like you see right there. So component form is where those are not parentheses. Might be a little unclear, but it looks like this, like a sideways V. So it says 3, 2. So when we look at component form, my horizontal component, which is in the x position, tells me what I'm doing left or right. So this is obviously going 3 to the right. And then the value that's in my y spot, my vertical component, tells me what I'm doing up or down. So this one tells me I am going up 2, since it's positive. So anyway, they want us to find component form of these following situations. So we can use what we call a scalar. A scalar is where you simply multiply the entire vector by a number. And that just means really just distribution. I'm going to multiply both components of vector v by 2. So if I multiply this one by 2, my new horizontal component becomes 10. If I multiply this guy by 2, I get negative 2, and that's my new vertical component. So here's kind of the way that looks. Here's sort of the general notation. It says k times vector v, right? So k just represents a scalar. That's what you're seeing right here. So a scalar is being multiplied by both components within the vector. Okay, and so that's why, so here's the general look. You have that says v sub 1, comma, v sub 2. So it's just saying that I'm basically multiplying my scalar times both components. So it becomes k times v1, comma, k times v2. We can add vectors together by simply adding their components together. So if I wanted to do u plus v, I would add up the x components, 3 plus 5, to get the new x component. We would add the y components, 2 plus negative 1, in order to get our new y component. So it looks like this. And then for the last one, so this one we're just doing 3 operations, I should say. I have a scalar here, I have a scalar here, then I will add the results. So we would start by multiplying the components of vector u by negative 2. So what's that going to become? Negative 6, negative 4. If I multiply vector v times 3, so 3 is our scalar, that becomes 15 comma negative 3. Now they want me to add those results together. Right? So after I did the multiplication of the scalars, I would then add those 2 vectors together the same way that I added right here. Right? And so you can take a look at part C, but that's the way that one played out. Let's try one on our own. So for this one, we have vector u is 2, negative 1. Vector v is 1, 3. Vector w is negative 1, negative 1. So the one I'm going to have us do is number 4, which says 3u plus 2v. Let me make that a little darker so you can see it. So 3u plus 2v. So that's what we're being asked to do. In other words, I'm going to multiply vector u times a scalar of 3. So if I multiply both components by 3, it becomes 6, negative 3. If I multiply my v vector by a scalar of 2, then my new numbers for that would become 2, 6. And now I would then add my results together. So if I add those together, again, I'm just going to combine the ones that go together. So my x's go together. 6 plus 2 is 8. Negative 3 plus 6 is 3. And then that's how we write it in component form. Piece of cake. That's pretty basic math on those. So let's see on this one. Here's a common question. Find a unit vector in the direction of v. So what they're telling me is it runs this direction. This is my horizontal component. This is my vertical component. Basically think of the idea of slope when you're doing this. But here's how we find a unit vector. To do a unit vector, you are doing the vector divided by its magnitude. So here's kind of the look, right? So if I'm going to do this to vector v, this is vector v. So I need to know what is vector v, and I'm going to divide that by its magnitude. So we're going to start out with just getting the magnitude of vector v, and it's basically Pythagorean theorem, right? Distance formula. We've seen that before, how distance formula is the Pythagorean theorem. Underneath this square root, so I'm just looking at my horizontal component squared plus my y component squared. And then all that's under a radical, just like distance formula. This is how far I'm going to the right. This is how far I'm going up or down. And we're just plugging those in and getting our magnitude. So it comes out to be the square root of 26. So the way we would find a unit vector is we would take each component and divide it by its magnitude so that it looks like this. So this is now a unit vector. In other words, now if I did the square root of a squared plus b squared, I'm going to get just a value of 1. That's why they call it a unit vector. So anyway, that's what the result would look like. Again, on this, guys, the idea is I am dividing the vector by its own magnitude. And as we know, what happens when you divide something by itself? It's 1. Right? That's why they call this a unit vector. So when you take a vector and divide out its own magnitude, right, it becomes a magnitude of 1 when you do that. So let me flip the page for you. So this was how they verified what I was just talking about. So here was the new horizontal component. Here's the vertical component. This is our unit vector. And the reason it's a unit vector is because now, if you plug that into your distance formula, so if I did a squared plus b squared all underneath the radical, notice it comes out to just be a value of 1. All right, so now it has a magnitude of 1. So let's try that with vector v here. So vector v says 3i plus 2j. So the reason I had you guys do this one is because this is a different notation. It's very similar to component form. I mean, it will mean the same thing. It just is a different way of writing it. So they use the letter I to represent the horizontal component. They use the letter j to represent the vertical component. So 3i plus 2j is the same thing as positive 3, positive 2 in component form. So this is component form. This is like I and j form. So it's just two different ways of writing it, but both of these mean the same thing. They're both referring to a vector with a horizontal component of 3 and a vertical component of 2. So if we're going to do the unit vector, first things first, we have to find the magnitude, which is just the square root of a squared plus b squared. So what's that looking like? 9 plus 4 is 13. So that is the magnitude. So if I divide each component by the magnitude, it's going to create a unit vector for us. So I'm going to write it as 3 over the magnitude and 2 over the magnitude. And there's our unit vector. So, and that's it. That's all there is to it. So there's our unit vector. Again, if I was to now do what they did here, and if I did the square root of a squared plus b squared, I would come out to be 1. And that's a way of, you could always check your answer by doing that. So let me come down to this one. Now we're going to throw a little bit of trig in here. I'm sure you guys have been missing it quite a bit. So for this one, they are asking us to find the components. Those are these guys, right? Your horizontal and your vertical components with the information that they're giving us. And what they're telling us on this one is it has a direction of 290 degrees. So you can see where they drew that vector. So as we start at 0, go to 290 degrees, that's where the vector is going to be drawn. They also said it has a length or a magnitude of 4 units. So you can see how they labeled it with a 4 right there for its length. So we got to use that information to find our components. So here's the way we're going to set this one up. So if you think back to all of our unit circle stuff, remember that cosine represented the x value and sine represented the y value. So within this scenario here, we're still back into sort of that trig idea. And so that's why it's simply the magnitude times the cosine of the angle would give us the horizontal component. The magnitude times the sine of your angle would give you the horizontal component, right? Or your y component. So what they did on this was, here's how they wrote it, right? They just plugged in the information that was given. They told us the magnitude was 4. That goes here. They told us the angle was 290. That goes there. And that's it. That's our setup. Okay, but now we do need to simplify it. So I need to know what is the cosine of 290 and multiply it by 4. That will give me the horizontal component. If I did the sine of 290 times 4, that gives me the vertical component. Of course, 290 is not a value that's on our unit circle. So this one just became a calculator problem. So if you went into your calculator, and of course we'd be in degrees, and you type in 4 times cosine of 290 degrees, that will give you your x component. And if you did 4 sine 290, that's going to give you this guy, which is your vertical component. And that's all they were looking for. So really just a formula. We are going to get a decent chunk of formulas throughout this chapter, so definitely want to highlight those, or something to keep track of the formulas that you're going to be getting throughout this chapter. So we're going to try one like we just did, given this information. Guys, sometimes they could, of course, give it to you in like a word problem. So as you look at number 20, they're just telling me what the direction and what the magnitude are, just like the one up above. They could also give it to me by just giving me a diagram. So as I look at this one, I'm pretty certain there was a bit of a typo on this problem. I don't think this arc is supposed to be here. If I was calling this 198 degrees, we already know that if I only went from here to there, it's 180 plus another 18 degrees gives me that 198. So I think this was an accident that they put this curve here. I already looked through the book problems and there were none that did this. So I think that's a bit of an accident. So ignore that little curve. Let's just cross it out. All right, so that's not really there. So what they're telling me is my direction is 198 degrees. Based on this guy, my magnitude is 17. So I'm going to use, again, this idea right here to find my components. So my magnitude was 17. That's going to go here. And my angle was 198 degrees. That's going to go here. So as we set this one up, I got my magnitude times the cosine of the angle. And for the vertical component, magnitude times the sine of the angle. And so that's really the setup for it. The rest is going to be calculator. So, of course, in this one, we are in degrees. So do make sure that you are in the right mode. So as I did 17 cosine 198, that would be my horizontal component. And as I did 17 sine 198, we got the vertical component. And that's it. So fairly simple on those. Moving on down to this guy, it says find the direction angle of a vector. So find the magnitude and direction angle of each vector. So magnitude we already know is the square root of a squared plus b squared. So the square root of 1 plus 16, which is 17. So the square root of 17 would be the magnitude. So how do we find the direction of this thing though? So as I consider my horizontal component as 1, positive 1, and my vertical component is positive 4, just remember the formula that we had up above. So they're telling me that this equals my horizontal component, so I'm going to set this equal to 1. This equals my vertical component, so I would set that one equal to 4. And so now, right, because that was our components that they gave us right here. So we'd be saying something like the magnitude, which is rad 17, times the cosine of theta is equal to 1. And then we have to solve for theta. And of course, that means we're using an inverse function in order to solve it. And we're going to be doing something real similar for the y. Let me just show you that one, and then we'll do some together. So again, so here was the setup, right? This is the formula that we used on the previous problem. So I'm going to set my horizontal component equal to this guy, and my vertical component, which is 4, equal to this guy. So we already figured out the magnitude was rad 17. So here's now the little side work that's going to go into finding the angle. So guys, notice on this, I really don't need both of these in order to figure out the angle. Right? I don't need both of them. I only need to do this with one of them. So I'm just going to pick one. So they just picked, let's just use the horizontal component. So they said that 1 is equal to this. So that's what you're seeing right here. And now we're just solving for A. So we divide over the magnitude, then we take the inverse cosine in order to get our angle. Guys, the angle would be consistent whether you use the horizontal or the vertical component. It doesn't matter. So that's why we just got to pick one of them in order to find it. So it's the same vector, means it has the same angle. So we just need one way of getting the angle. We don't have to do it with both components. So just peek at how they did the next one. So again, same formula. They set -5 equal to the magnitude times cosine of beta. And they set the 4 equal to magnitude times sine of beta. So first thing that we got to do is figure out what's our magnitude. So what goes into this slot right here? And that's where you're doing your square root of a squared plus b squared. And we get rad 41. So again, that's what they're doing. They're setting the horizontal component equal to -5, but now subbing in rad 41 for the magnitude, and then just solving that equation. Of course, that ends with an inverse function, since you're trying to find an angle. So we're going to skip that guy for part C, but you get the idea. And again, we could have done this with either the horizontal component or the vertical. They just chose to use the horizontal one. So we could have just as easily said 4 is equal to magnitude sine beta, and then solve that equation. And if we did this all correctly, we should get the same answer that we got right there. So let's try one of those. So find the magnitude and direction. Now, that's kind of a helpful hint, because if it just said find the direction, well, as you just saw, I got to know the magnitude anyway. So by them saying find the magnitude and the direction, it's kind of a hint as to how to proceed. So let's just start with finding the magnitude. So we're going to do this with number 29 here. So vector u. And again, magnitude, if you put the little absolute value brackets like I just did, that means magnitude. Square root of a squared plus b squared. So 36 plus 16 is 52. I'm just going to leave it like this for right now. So there's our magnitude. So now, again, I'm going to say that 6 is equal to magnitude cosine theta. And that's the setup we're using to solve for our missing angle here. So if I divide this guy over, so 6 over rad 52 is equal to cosine theta. So I'm just going to simply do the inverse of my fraction in order to get the angle. So about 33.7 degrees would be our angle. Not so bad, I don't think. Because like I mentioned though, all this comes back to formulas, right? So as you're getting formulas like this, that we've already talked about, not a bad idea to either maybe highlight all your formulas in one color, or you could even make a list of your formulas on a separate piece of paper. Whatever helps you later on is whatever you should be doing here. So let's finish this out with little word problems. So I know you guys love word problems. So here we go. Jet is flying on a bearing of 65 degrees at 500 miles per hour. Find the component form of the velocity of the plane. So as we're looking at this, 65 degrees in terms of bearings, as we've already discussed, is measured from the north, right? So my bearing of 65 degrees looks like this. So that is my 65 degrees. So in terms of vectors though, right? Vectors are measured like you would measure an angle from the unit circle. They're measured from 0. So this is really the angle of the vector that we want to look at. Well, if this is 65, what does that make this angle? So this guy is going to have to be my 25 degrees. And so now I know the direction of it is my 25 degrees. And now we're going to come up with, so if it's going at 500 miles per hour, right, that means in 1 hour it has traveled 500 miles. So that 500 miles of travel is its distance or its length or its magnitude, right? Same thing. So let's just write that one down. All right, so as we just saw, if I want to get the sort of the component form of this guy, component form looks like this. And as we just saw, it's the magnitude times the angle. Gives us the horizontal component. And then it's magnitude times the sine of the angle. Gives us its vertical component. So in other words, what we're seeing on this is, once I get some decimals out of this, I'll punch this into the calculator, but as it goes 500 miles in the first hour, this is how far it went to the right. This is how far it went up, right? So those two components, when you put them together, create this vector right here. So anyway, you could type those into your calculator. I know you can do that part from here as we just did on the last one. One thing I wanted to remind you guys though of is, remember, there's another way you can write these in terms of I and J. So when you do I and J, then we would leave out the sideways V's on this, and we could say something like 500 cosine 25 I to represent the horizontal component, plus our vertical component, which is our 500 sine 25 J. So just want you guys to keep recognizing different ways of writing this. So you have the component form, and then you have your I and J form that looks like this. So if you still want to hang out for a few more minutes, we're going to take a look at example 8 on page 454. So here is example 8. So this one is discussing the effect of wind velocity. This one's kind of an interesting one because this is something we would take into account, like if you were, say you wanted to swim across a river, right? And you just wanted to go directly across, straight across to the other side. Well, if the river is flowing downstream, right, you can't swim directly across, or you'd end up lower down on the riverbank from where you wanted to be when you finally got there. So, right, you have to swim upstream a little to fight the current in order to actually get straight across on that river, right? So the same thing is true when, say, you fly an airplane, right? So when an airplane takes off, they have to take into account the wind and how the wind is going to affect their path, and they have to adjust their headings for that. So here's what's going on. We have this airplane taking off. The airplane wants to go on this path right here, AD, right? It wants to go directly to the east. And so that would be fine if there was no wind. They would just set their bearing at 90 degrees, right? This would be a 90-degree bearing because bearings measure from the north. So we would just have a 90-degree bearing if there was no wind. But with this problem, they're saying, but there is wind, right? The wind has a bearing at 60 degrees, so that's the direction that the wind is blowing, and it's blowing at 65 miles per hour. So that's also going to push the plane not only this direction, but it's also going to make it go faster than normal too, right? Because now it has some wind behind it, making it go even faster. So this plane on its own would typically go 450 miles per hour, but with some of that wind behind it, it's actually end up going to go faster. So they want us to do two things here. They want us to figure out what bearing should this plane head so that when you mix it with the wind, it is now on the path of AD. So if they're calling this vector V, right, that's AD. So AD is the path we want to be on. AC is the wind, and AB is the path the plane is actually going to have to travel, so that when you add the wind to it, its path will be AD. All right, so hopefully that makes sense, but again, it's going to have to fly a little this direction in order to counter the wind that is trying to push it this direction, so that when you put those two things together, it's going this way. So it just wants to go straight east, and that's it. So let's look at a couple things. So we know that AD, which is the path that we want to go down, is the sum of vector AB plus AC, right? So the bearing of the plane mixed with the wind should put it onto this path right here. So we're adding those two vectors together. So we're trying to find the bearing of AB, right? This one right here. So we want to know, okay, if this plane's going to take off under these conditions, what bearing should it travel towards so that when the wind is added on, it will go true east? That's the goal. So we're trying to find that bearing right there. So the one angle we don't yet know is that little theta right there. So that's the first thing that we're going to find. So if you look at AC, the wind, going back to the form that we just looked at, we know its magnitude of 65, and we know the angle that is traveling is 30 degrees. So one thing that's tricky about this problem, and you really got to be careful with this, is the way the measurements were given to us, they were giving us bearings, right? They had a bearing of 60 degrees, and bearings are measured from the north. However, when you use this formula, the angles that you see here are measured from 0, right? Like in the unit circle. And so if my bearing was 60, I know that this angle right here from 0 would be 30. And so that's the one that made it into the setup that you see right here. So there's the vector of AC, which is the wind. The vector of the airplane, again, this one's traveling at 450 miles per hour, so 450 is the magnitude, but we don't know this angle. And so that's what we have to figure out, is what is theta. So here's the setup for AB. Notice they just left theta as theta because we don't know what that is yet. If I add this vector to this vector, it's going to look like this, right? So if I did the two x's added together, that's what you see for the first half of this right there. And if I were to add the vertical components together, that's what I'm seeing for the second half of this, which is right there. So remember, in order to find the angle that I'm looking for, I only need one of the components. If this plane is to travel like a true east direction, well, on that path, there would be a 0 vertical component, right? Because if it goes true east, it's only going to the right. It's not going up or down, which means I can take the vertical component, which is this guy, and set it equal to 0, which is what you're seeing right here. And that was their setup that they then were just solving for theta. So you subtract this over to the other side, divide by 450. We do the inverse sign in order to come up with our angle. So that little theta that you see right there is at a negative 4.14 degrees. So the question they asked on this one, though, is what is the bearing? So if that is negative 4.14, that is measured from 0. The bearing would measure from the north. So from here all the way to that blue line would be the bearing. So essentially we need to take this 90 degrees, tack on another 4.14, and that's what we get right here for the bearing of this airplane. The one other thing they asked us to find on this was the ground speed. In other words, how fast is it going compared to the ground, which is still. So the wind by itself, if there was the plane by itself, if there was no wind, would travel 450 miles an hour. But with some wind behind it, now it's going to go even faster, right? And so that's what we're looking at for this bottom piece. So if you look back at the beginning of my notes when we first introduced the idea of magnitude, one of the words I put into that was speed, right? So when they talk about the speed of this plane, that is the magnitude of the vector that the plane is traveling on. So just finding the magnitude of this airplane here. So here was vector AD, that's the path of our airplane. So again, I'm just doing the square root of a squared plus b squared. So the horizontal component squared plus the vertical component squared, right? And all that's really just calculator stuff from there. So if we throw all that into our calculator, I get the ground speed, or how fast the airplane is traveling compared to the ground that it's flying over. And that is it for that one.